Hello everyone, and welcome to Stuff I Found Interesting. Today's rabbit hole is nuclear fission. My last video highlighting nuclear propulsion engines sparked a further interest into the nuclear fission process itself. In this video, I will be going over what nuclear fission is, what amount of energy is generated by the process, what energy we can harness, why it is comparatively clean energy, use cases, and downsides. I will also include what I think would happen should we swap to a primarily nuclear-focused energy sector. After looking into it more, it seems a bit strange that we do not use nuclear energy for more of our overall energy needs. Yes, there were disasters in Chernobyl and Fukushima. Current nuclear power plants have learned from those mistakes, and they have changed layouts, inspections, how they handle extra heat, and added numerous fail-safes to take over should something fail. Those disasters are highly unlikely to happen again, short of something catastrophic and unforeseen happening. That is something that could be said for any of our energy sources. Nuclear fission is a process in which the nucleus of an atom is split into two or more smaller nuclei, along with the release of a large amount of energy. This reaction is caused by the absorption of a neutron by the nucleus, which results in the nucleus becoming unstable and breaking apart. The energy released in nuclear fission can be harnessed for various purposes, such as generating electricity in nuclear power plants or powering nuclear weapons. The amount of energy generated in a single nuclear fission reaction can be substantial, typically in the range of millions of electron volts. For comparison, the energy released from the chemical reactions in a typical battery is on the order of a few electron volts. The exact amount of energy released depends on the specific isotope undergoing fission and the conditions of the reaction. In a nuclear power plant, multiple fission reactions are continuously taking place, releasing a large amount of energy that can be harnessed to generate electricity. The process of getting fissionable material to generate electricity that is fit for the electrical grid involves several steps: obtaining fuel, loading fuel into a reactor, starting the reaction, generating heat, turning the steam into electricity, and disposing of the waste products. Nuclear fuel typically consists of enriched uranium or plutonium, which are isotopes capable of undergoing nuclear fission. The fuel is produced through a process called enrichment, in which the concentration of the fissile isotope is increased. The fuel is loaded into a nuclear reactor, which is designed to control and sustain a chain reaction of nuclear fissions. The chain reaction of nuclear fissions is initiated by introducing a neutron into the reactor. This neutron collides with the nucleus of the fuel, causing it to split and release more neutrons, which in turn causes more fissions to occur. The reaction is controlled by adjusting the rate at which neutrons are introduced, and by using neutron-absorbing control rods to regulate the reaction. The energy released from the nuclear fissions is in the form of heat, which is used to generate steam. The steam is used to drive a turbine, which generates electricity. The electricity is then transformed and transmitted into the electrical grid, where it can be used to power homes and businesses. After the fuel has been depleted, it is considered waste and must be disposed of safely. Spent nuclear fuel still contains isotopes that are radioactive and must be handled and stored with care to prevent the release of radioactive material into the environment. There are currently two main ways to dispose of the waste product from nuclear power generation. The first is called dry cask storage. This method involves storing spent nuclear fuel in specifically designed containers known as dry casks that are made of thick concrete and steel. The containers are designed to withstand natural disasters and provide long-term safe storage for the waste. The second is a geological repository. This method involves permanently burying the spent nuclear fuel in a deep geological repository, such as a salt dome or deep mine. The spent fuel is placed in a sealed container and placed in a repository deep underground, where it is isolated from the environment for hundreds of thousands of years. Both of these methods have been used successfully in various countries, and both have their advantages and disadvantages. The choice of which method to use ultimately depends on various factors, including the specific geological and geotechnical conditions at the site, the national policies and regulations, and public acceptance. Since the accidents at Chernobyl and Fukushima, there have been significant improvements made to the design and safety of nuclear power plants. Some of the key changes include enhanced safety systems, improved emergency preparedness, better reactor designs, stricter regulations, and increased transparency and public engagement. Nuclear power plants now have multiple safety systems in place, including backup power supplies, containment structures, and cooling systems to prevent accidents and mitigate their consequences in the event of a failure. The industry has also focused on improving emergency preparedness and response capabilities, with the development of plans and procedures for responding to accidents and ensuring the safety of the public and the environment. There have been significant improvements in the design of nuclear reactors, with a focus on enhancing safety and reducing the risk of accidents. This has included the development of advanced passive cooling systems, which rely on natural forces to cool the reactor in the event of a failure, rather than relying on active cooling systems that require power to operate. One of the key causes of the Fukushima accident was the loss of power to the cooling systems, which led to the overheating of the reactors. New reactor designs incorporate multiple independent backup cooling systems to ensure that the reactors can be safely cooled cooled in the event of a loss of power. New reactor designs also include improvements in the management of spent fuel, including enhanced storage facilities, increased safety features, and improved fire protection systems. The regulations governing the operation and safety of nuclear power plants have been strengthened in many countries, with more stringent requirements for licensing, inspection, and enforcement. There has also been greater emphasis on transparency and public engagement, with more information being made available to the public about the safety and operation of nuclear power plants, and increased opportunities for public involvement in decision-making processes. The Fukushima accident in particular highlighted the need for improved seismic design of nuclear reactors. As a result, new reactors are being designed to withstand larger earthquakes and other seismic events, with a focus on ensuring the structural integrity of the containment building. Overall, these improvements have helped to enhance the safety and reliability of nuclear power and to increase public confidence in the technology. However, the safety of nuclear power plants will continue to be a concern and area of focus for the industry, and further improvements and advancements will likely be made in the future. The amount of energy that is wasted between the fission reaction and getting electricity to the grid can vary depending on the specific nuclear power plant and the conditions under which it operates. However, it is typical for about 1/3 of the energy generated by the fission reaction to be lost as waste heat. The primary cause of energy loss is the inefficient conversion of heat to electricity. In a typical nuclear power plant, the heat from the fission reactions is used to generate steam, which drives the turbine to generate electricity. However, some of the heat is lost during the conversion process due to the inefficiencies of the turbine and generator. In addition to the losses in the conversion process, there are also losses associated with transmitting the electricity from the power plant to the electrical grid. These losses can be caused by resistance in the transmission lines and transformers, as well as other factors such as weather conditions and the distance the electricity must travel. Overall, while some energy is inevitably lost in the process of generating and delivering electricity from the nuclear power plant, the vast majority of the energy generated by the fission reaction is still usable and can be put to work to power homes and businesses. There are several ways to mitigate some of the waste heat generated in a nuclear power plant. They are improved thermal efficiency, combined heat and power, waste heat recovery, and district heating. One of the most effective ways to reduce waste heat is to improve the thermal efficiency of the power plant so that more of the heat generated by the fission reaction is converted into useful electricity. This can be achieved through the use of more efficient turbines, generators, and other components, as well as through better design and optimization of the plant's systems. Another way to reduce waste heat is to use it for other purposes, such as heating or cooling. This can be achieved through combined heat and power systems, which use the waste heat from the power plant to generate electricity, as well as provide heat and cooling for homes and businesses. Another strategy is to use the waste heat to generate electricity through the use of waste heat recovery systems, such as organic Rankine cycle systems, which convert the waste heat into electricity using the heat exchanger in the turbine. Another option is to use the waste heat from the power plant to provide district heating for nearby homes and businesses, using a network of pipes to distribute the heat. This can be a cost-effective way to utilize the waste heat and reduce the overall energy losses of the plant. Overall, these strategies can help to reduce the amount of waste heat regenerated by a nuclear power plant and to increase the efficiency and effectiveness of the plant's operations. However, the specific measures that can be taken will depend on the specific conditions and requirements of each individual plant, and the most effective approach will depend on a range of technical, economic, and regulatory factors. I dove a bit deeper into the combined heat and power method of dealing with the waste heat. I found that these systems, also known as cogeneration systems, are energy systems that generate both electricity and useful thermal energy in a single integrated process. They are designed to be highly efficient, reducing the amount of energy that is lost as waste heat and improving overall energy efficiency. In a combined heat and power system, the heat generated during the electricity generation process is recovered and used for other purposes, such as heating buildings or generating additional electricity. This helps to increase the overall efficiency of the energy system, reducing the losses and reducing the greenhouse gas emissions. Combined heat and power systems can be based on a variety of technologies, including internal combustion engines, steam turbines, and gas turbines. They can be designed to meet the specific energy needs of a particular facility and can be scaled to meet the needs of homes, businesses, or entire communities. The benefits of these systems include increased energy efficiency, improved energy security, cost savings, and reduced greenhouse gas emissions. By using the waste heat from the electricity generation process for other purposes, these systems can increase the overall efficiency of the energy system as a whole, reducing energy losses and improving energy efficiency. These systems can also provide a reliable and secure source of energy, reducing the reliance on energy imports and improving energy security. By reducing the energy losses and increasing the energy efficiency, these systems can result in cost savings for the operator and the users of the energy system. By reducing the amount of energy that is lost as waste heat, these systems can reduce greenhouse gas emissions, helping to mitigate the impacts of climate change. Overall, combined heat and power systems are a flexible and cost-effective way to improve energy efficiency and reduce energy losses in a wide range of applications, and they are increasingly being used in a variety of settings, including homes, businesses, and industrial facilities. After looking into what combined heat and power systems could do to benefit our nuclear power plants, I took a deeper look into the various waste heat recovery systems that are out there. Waste heat recovery systems are technologies that capture and use the waste heat generated by the industrial processes and energy systems for the production of electricity. The goal of these systems is to reduce energy losses and increase overall energy efficiency by converting waste heat into useful energy. Waste heat recovery systems can be based on a variety of technologies, including steam turbines, internal combustion engines, and organic Rankine cycle systems. The specific technology used will depend on the characteristics of the waste heat source, including temperature, pressure, and flow rate. In a Rankine system, the waste heat is captured and used to heat a working fluid, typically a refrigerant, which is then used to generate electricity in a turbine. The working fluid is then cooled and the cycle repeated. Organic Rankine systems are well suited for low temperature heat sources and are widely used in a variety of applications, including industrial processes, power plants, and transportation systems. Waste heat recovery systems are a flexible and cost-effective way to improve energy efficiency and reduce energy losses in a wide range of applications. Nuclear energy is considered to be comparatively clean to its alternatives, such as fossil fuels, for several reasons. Unlike fossil fuels, nuclear energy does not release greenhouse gases, such as carbon dioxide, during the energy production process. This makes nuclear energy a cleaner alternative for reducing greenhouse gas emissions and mitigating the impacts of climate change. Nuclear power plants require less land compared to other energy sources such as wind or solar power for equivalent energy production. Nuclear energy is highly energy dense, meaning that a small amount of fuel produces a large amount of energy. This makes nuclear energy a compact and efficient source of energy compared to other sources. Unlike fossil fuels, which emit pollutants such as sulfur dioxide and nitrogen oxides, nuclear energy does not produce air pollution during the energy production process. Unlike renewable energy sources such as wind and solar, which are dependent on weather conditions, nuclear energy is a stable source of energy that can provide consistent power to the grid. However, it is worth noting that the production and disposal of nuclear waste, as well as the potential risk of accidents, remain challenges that need to be addressed. Nevertheless, compared to its alternatives, nuclear energy is considered to be a relatively clean source of energy, especially in terms of its low greenhouse gas emissions. Nuclear energy and nuclear power plants have several disadvantages. Nuclear energy produces radioactive waste that remains highly dangerous for hundreds of thousands of years and is difficult to dispose of safely. The potential for accidents at nuclear power plants and the release of radioactive materials pose significant safety concerns for nearby communities and the environment. The technology used for nuclear energy production can also be used for the development of nuclear weapons, which raises proliferation risks and contributes to global security concerns. Building and maintaining nuclear power plants is expensive, and the costs can be substantial. Nuclear energy relies on the availability of nuclear fuel, and reserves of this fuel are finite, making it an unsustainable energy source in the long term, similar to fossil fuels. There is often significant public opposition to the construction of new nuclear power plants, largely due to safety and waste concerns. Building a nuclear power plant can take many years, and the lengthy permitting and construction process can be time-consuming and complex. Despite these disadvantages, nuclear energy remains an important source of energy for many countries, providing a reliable source of low-carbon energy. Efforts are underway to address these challenges, such as developing safer reactor designs, improving waste management techniques, and reducing the risk of proliferation. Switching to nuclear energy as the primary source of power could bring several potential global benefits. Nuclear energy produces low greenhouse gas emissions, especially compared to fossil fuels, which would help reduce the impacts of climate change. Nuclear energy is a stable source of energy that can provide consistent power to the grid. This reduces the need for energy storage and the need for energy from fossil fuels during periods of low renewable energy generation. Nuclear energy is highly energy dense, meaning that a small amount of fuel produces a large amount of energy. This makes nuclear energy a compact and efficient source of energy compared to other sources. Nuclear energy can reduce dependence on energy imports, increasing energy security and reducing the vulnerability of countries to fluctuations in energy prices and supply disruptions. The construction and operation of nuclear power plants can create jobs and stimulate economic growth. However, it is important to note that transitioning to nuclear energy as the primary source of power would also bring several significant challenges and require significant investments in research, development, and infrastructure. Additionally, the production and disposal of nuclear waste, as well as the potential risk of accidents, would also need to be addressed. I believe that transitioning to a more nuclear-focused energy production infrastructure will have lasting benefits for everyone. The fact that such a small amount of base material can produce large quantities of power is something that we should be taking advantage of. If energy becomes cheap, how many more things could we keep powered for longer? We would lower the costs of just about any service that we use, since the overhead for all of those companies would drop. Supercomputers solving serious problems would be able to run for longer or at higher speeds. Household costs would drop, freeing up more disposable income for the average person or family. We, as a society, need to get over our fear of nuclear power. Yes, accidents happened in the past. Like with any disaster, we need to learn from our mistakes and move forward. As long as both public sentiment and the interests of established established energy companies do not change, we will not be able to move forward towards a better way of doing things. Thank you for listening. I hope you liked learning alongside me. Please let me know if I missed anything or got anything incorrect, as I would love to learn more. The privilege of your time means a lot to me. No matter who you are, you only get 24 hours in a day. Thank you for spending a portion of it with me. See you next time.